Advanced Engineering Physics. Unit 1. Crystallography and Materials Characterization. Defects in crystals. In our previous discussions, we studied crystal structures assuming that atoms are arranged perfectly in a regular and periodic manner. Such an arrangement is called an ideal crystal. However, in reality, perfectly ordered crystals do not exist. Every real crystal contains irregularities or imperfections in its atomic arrangement. These imperfections are known as crystal defects. An ideal crystal is a theoretical model in which atoms are arranged perfectly according to one of the crystal structures and extend infinitely in all directions without any disturbance. Every atom occupies its exact lattice position, and the periodic arrangement continues throughout the crystal. Real crystals, however, always deviate from this ideal behavior. Some atoms may be missing from their normal positions. Some may occupy incorrect positions, and tiny cracks or microscopic fissures may be present inside the material. Even the external surfaces of crystals are not perfectly flat. All these deviations from perfect periodicity are collectively called crystal defects. At first glance, defects may appear to be undesirable flaws, but surprisingly, defects play an extremely important role in determining the physical properties of materials. The strength of metals, the conductivity of semiconductors, the diffusion of atoms, the color of crystals, optical properties, and luminescence are all strongly influenced by the presence of defects. Depending on the dimensions over which they exist, crystal defects are classified into 4 categories. Zero-dimensional defects are called point defects. Let us begin with point defects. Point defects are localized imperfections involving only one or a few atoms. Since they are confined to a very small region, they are called zero-dimensional defects. The concentration of point defects depends strongly on temperature. As temperature increases, atoms gain thermal energy and are more likely to leave their normal positions. Therefore, the number of point defects increases with temperature. 2 important types of point defects are Schottky defects and Frenkel defects. Let us first discuss Schottky defects. A Schottky defect is also called a vacancy defect. It occurs when an atom or ion is completely missing from its normal lattice site. Imagine a perfectly arranged crystal lattice in which every position is occupied by an atom. If one atom gains sufficient energy and moves from the interior of the crystal to its surface, the original lattice site becomes empty. This empty position is called a vacancy. In ionic crystals, electrical neutrality must be maintained. Therefore, positive and negative ions usually leave the lattice in pairs. As a result, equal numbers of cations and antions are absent from their lattice positions. Since atoms are removed from the crystal interior, while the overall volume remains almost unchanged, the density of the crystal decreases. Schottky defects are commonly found in ionic crystals such as sodium chloride, potassium chloride, and cesium chloride. The number of vacancies present at thermal equilibrium depends on temperature and is given by an exponential relation. The equilibrium number of vacancies, n, is approximately equal to n multiplied by exponential of minus EV divided by Ki dt. Here, n is the total number of lattice sites, EV is the energy required to create a vacancy, Kb is the Boltzmann constant, and T is the absolute temperature. This equation shows that as temperature increases, the number of vacancies increases rapidly. Now, let us discuss Frenkel defects. A Frenkel defect occurs when an atom leaves its normal lattice site, but remains inside the crystal by occupying an interstitial position. An interstitial position is an empty space between the regular lattice sites. In this defect, an atom is not removed from the crystal. Instead, it is simply displaced from its original position to an interstitial site. As a result, the total mass and volume of the crystal remain unchanged. Therefore, the density of the crystal does not change. Frenkel defects are more common in ionic crystals, where one of the ions, usually the smaller cation, can easily move into an interstitial position. Silver bromide and silver chloride are typical examples of crystals exhibiting Frenkel defects. The equilibrium number of Frenkel defects is given by the relation n is approximately equal to square root of n multiplied by n prime multiplied by exponential of minus ei divided by 2 kbt. Here, n is the number of normal lattice sites, n prime is the number of interstitial sites, I is the energy required to create the defect, and T is the absolute temperature. Thus, both Schottky and Frenkel defects arise due to thermal motion, but they differ significantly in their effect on density. Schottky defects decrease density because atoms are missing from the crystal. Frenkel defects do not affect density because atoms remain within the crystal. Now let us move to line defects. Line defects are also known as dislocations. Unlike point defects, which involve individual atoms, line defects extend along a line inside the crystal. Dislocations are extremely important because they explain why metals can be bent, stretched, and shaped without breaking immediately. If crystals were perfectly ordered, they would require extremely high forces for deformation. However, real crystals contain dislocations, and these dislocations can move under applied stress. This movement allows plastic deformation to occur at much lower stresses. Thus, dislocations are responsible for the ductility and malleability of metals. To describe a dislocation quantitatively, crystallographers use a vector known as the Berger's vector. Imagine drawing a closed path around a defect inside a crystal. Now, perform the same sequence of steps in a perfect crystal. The path fails to close because of the distortion introduced by the dislocation. The vector required to close the path is called the Berger's vector. It represents both the magnitude and direction of the lattice distortion caused by the dislocation. There are two fundamental types of dislocations: edge dislocations and screw dislocations. Let us first discuss edge dislocations. An edge dislocation is formed when an extra half plane of atoms is inserted into the crystal lattice. Imagine a stack of perfectly arranged atomic planes. Now insert an extra plane that extends only halfway through the crystal. The line where this extra plane terminates is called the edge dislocation. The atoms above this line are compressed, while those below are stretched. This creates a distortion field around the dislocation. For an edge dislocation, the Berger's vector is always perpendicular to the line of dislocation. This perpendicular relationship is one of the key characteristics used to identify edge dislocations. Now, let us discuss screw dislocations. A screw dislocation is formed when part of the crystal is cut and sheared by one atomic spacing. Instead of remaining as flat layers, the atomic planes become twisted into a spiral or helical shape around the dislocation line. The arrangement resembles the threads of a screw, which is why it is called a screw dislocation. For a screw dislocation, the Berger's vector is parallel to the dislocation line. This is the opposite of the relationship observed in edge dislocations. Screw dislocations play a very important role in crystal growth. The spiral structure continuously provides steps where new atoms can attach. Therefore, crystals can grow efficiently even when the surrounding environment contains only a small amount of material. This mechanism is responsible for the growth of very thin and extremely strong whisker crystals. Now let us discuss surface defects. Surface defects are two-dimensional imperfections that occur at the boundaries between different regions of a crystal. One important example is the small angle grain boundary, also called the tilt boundary. Sometimes, two neighboring crystal regions are not perfectly aligned. Instead, one region is slightly tilted with respect to the other. The boundary separating these regions consists of a regular array of edge dislocations. The angle of misorientation between the two crystal regions is represented by theta. If B is the Berger's vector and D is the spacing between neighboring dislocations, then the angle theta is given by theta equals B divided by D. This relation shows that the misorientation angle depends directly on the spacing of dislocations. Another important surface defect is the stacking fault. To understand stacking faults, let us recall the arrangement of atomic layers in close-packed structures. In a face-centered cubic crystal, the layers are stacked in the sequence A, B, C, A, B, C, and so on. In a hexagonal close-packed crystal, the stacking sequence is A, B, A, B, A, B, and so on. Sometimes, due to disturbances during crystal growth, the normal stacking sequence is interrupted. For example, an FCC crystal may accidentally develop an HCP sequence for a few layers. This irregularity in the stacking order is called a stacking fault. Stacking faults influence mechanical properties, especially the deformation behavior of metals. Another important surface defect is the twin boundary. A twin boundary is a special plane that separates two crystal regions that are mirror images of each other. In other words, one part of the crystal appears to be reflected across the twin plane. The atomic arrangement on one side is symmetrical to that on the other side. Twin boundaries are commonly formed during crystal growth or during plastic deformation. They influence the mechanical strength and deformation characteristics of materials. Finally, let us discuss volume defects. Volume defects are three-dimensional imperfections extending over a large region inside the crystal. These defects include voids, cracks, fissures, and inclusions. Voids are empty spaces inside the crystal. Cracks and fissures are large fractures that weaken the material. Inclusions are foreign substances trapped inside the crystal during its formation. These inclusions may be solid impurities, tiny liquid droplets, or trapped gas bubbles. Volume defects significantly affect the strength, toughness, and reliability of engineering materials. To summarize, real crystals are never perfect. They always contain defects of various types. Point defects involve individual atoms and include Schottky and Frenkel defects. Line defects are dislocations that enable plastic deformation in metals. Surface defects occur at boundaries between crystal regions and include grain boundaries, stacking faults, and twin boundaries. Volume defects are large-scale imperfections such as voids, cracks, and inclusions. Although defects represent deviations from perfect order, they are not merely flaws. In fact, many important physical and mechanical properties of materials are controlled by these defects, making their study one of the most important topics in crystallography and materials science.